All right, we're going to finish chapter 11 today, chapter 12 the next 2 days. Then that is the end of the material for this semester. All right, talk about intermolecular forces. All right, and so there's 3 types that we're going to talk about. First one is van der Waals. So the van der Waal, that is a type of force that will be broke up into 2 forces, which is going to be a dipole-dipole. And this is if you have a polar molecule. London, all molecules. So if you did your molecular molecular dipole, if it's polar, then it has dipole-dipole. Every molecule has London forces. Larger, more London. Then the third type is going to be hydrogen bonding. So it's up here. If you're polar, you got dipole-dipole force. Every molecule has London force. Hydrogen bonding is the third. So let's number them this way. London force, I always put as number 1 because every molecule has it. Number 2, I will put as the dipole-dipole force. Now, those 2 together are called van der Waals forces. All right, and then down here you have hydrogen bonding. So instead of 1, A, and B, let's go with 1 is London, 2 is dipole-dipole, 3 is hydrogen bonding. Anytime you're doing intermolecular forces, those are the 3 things you have to look for. All right, and so more intermolecular forces, higher the boiling point. So you're going to have 2 molecules, and they're going to say which one has a higher boiling point. So let's go CH3, CH2, CH3 versus CH3, oxygen, CH3, and then CH3, CH2, OH. All right, so anytime you are just carbons and hydrogens, you are non-polar. All right, so only London forces here. Anytime you have 1 electron pair, and most of the time when you have 2 electron pairs, you cannot be symmetrical. And this has the same structure as water. This is bent. So if you put an H on this side and an H on this side, it's water and you're bent. Same structure for CH3 on both sides of an O, and it is polar. And so this one has London because everything has London, and this has the dipole-dipole. All right, so now we didn't talk about hydrogen bonding. Hydrogen bonding, what you're looking for is you're looking for OH or NH. If you have an OH bond or an NH bond, you have hydrogen bonding. Note HF also has hydrogen bonding, but this is 1 molecule. All right, you can have an infinite number of OHs, infinite number of NHs, 1 molecule HF. So HF does have hydrogen bonding, but HF is only the 1 molecule hydrogen fluoride gas. All right, so you see that you have hydrogen bonding. If you have hydrogen bonding, you are also always polar. And you always have London. So this has all 3. This has London, dipole, dipole, and it has hydrogen bonding. And the boiling point here is about 78 degrees Celsius. The boiling point here is about minus 20 degrees Celsius. And the boiling point here, I don't even know, minus 40, I'm guessing. All right. And so you have only London forces. You're going to have a very low boiling point, minus 40 degrees Celsius. You have London and dipole. It's going to be higher, so it's minus 20. And again, I'm kind of guessing on these temperatures. And then your alcohol here would have a boiling point of 78. So note that an OH will increase the boiling point here by almost 100 degrees Celsius. All right. So they do give the energies. All right. Your London forces are very small, 0.1 to 10. That's also your dipole. Those are very small intermolecular forces. Your hydrogen bonding is much larger because they go from 10 to 40 for the energy required to break that interaction. And you're boiling it. You're breaking those interactions before it can boil off. All right, so you'll be given some compounds and you're going to be asked which one has the higher boiling point. And you do that by doing the London, the dipole, and the hydrogen bonding. The one with all three will have the highest boiling point. The one with only one of them will have the lowest boiling point. All right, so a London force is just an induced dipole force. So at any given time, more electrons will be on one side than the other side. And then that nonpolar neon atom will interact with another neon atom, and it will shift its electrons to line up with the other one. Delta plus, delta minus, always attracting each other. And so it is a nonpolar atom, but it can be induced to have a dipole that is called the London force. So they are very weak, right? London forces are very weak. The larger the molar mass, the more London forces. All right. If you have the same molar mass, then the one that has the most surface area has the higher boiling point. And so here we have a surface of 5 carbons in a row. This one, they all have 5 carbons and 12 hydrogens if you add them up. This one has a surface of 4. And this one has a surface of 3. All right, and so they're all nonpolar. So this one has London only. This one has London only. This one has London only. These are nonpolar carbons and hydrogens. These are called hydrocarbons. They are nonpolar. All right, and they all have the same molar mass. So they have the same molar mass. So it's now about surface area. All right, so the one that has more surface area, one that has more carbons in a straight line is going to have a higher boiling point. So this one has a boiling point of 36. When you go down to 4 carbons in a row, the boiling point goes down to 28. And you only have 3 carbons in a row, then it goes down to 9.5. All right, so London forces depends on the size of the molecule. When they are exactly the same size, the exact same molar mass, then you're looking at the surface area. All right, so the one that has the most atoms in a line is the one that is going to have the higher boiling point. Things coming off are called branches. So they'll talk about things branching off. So if you have, these all have 5. This one has 1 branch of a carbon going down. This one has a branch of a carbon going up and down. All right, so the one that has the fewer branches, the one that goes straight in a line, is going to have the highest surface area, which will give you the highest London force, which gives you the highest boiling point. All right, let's see thing here. We're not going to go through vapor pressure, although you need to know what you need to know about vapor pressure is higher temperature has a higher vapor pressure. So if you have cork on your water and you start boiling it, you're going to increase the pressure until the cork pops off the top. So here, what you need to know about vapor pressure: higher temperature, higher vapor pressure. All right, and so when we talk about vapor pressure, it's usually in millimeters of mercury. Surface tension, we're not going to talk much about surface tension, although water has a very large surface tension, and that's because water has a lot of hydrogen bonding. And so these molecules stay very close together because they are all interacting with hydrogen bonding. And so the H of another water molecule interacts, these dotted lines indicate hydrogen bonding. The O with the other water molecules interact with the H. And so one water molecule here, so this one water molecule, the one I started with, has 4 hydrogen bonding interactions. So one water molecule has 4 hydrogen bonding interactions. All right, so each of the hydrogens on it and each of the electron pairs on that O have a hydrogen bond to another water molecule. All right, so that's going to have a very good surface tension. So this is a very large surface tension. And so 7.3 times 10 to the minus 2, that is the largest surface tension of all of your compounds listed on this table. The next closest here is a glycerol, which also has a lot of hydrogen bonding, but it only gets up to 6.3 times 10 to the minus 2. All right, so water has a very high surface tension. You got lots of bugs that can walk across the top of water. All right. Viscosity, the only thing we're going to talk about viscosity is when you talk about, it's just about the flow of the liquid. If it is very slow, like molasses, then you have a very viscous liquid. If it pours out very nicely, like water just pours right out, it has a very low viscosity. Glycerol, it has a very large viscosity. So if you look at this chart here, this is the largest viscosity. So glycerol is it's very thick liquid. And so you know glycerol, then you know that. If not, you can look at these numbers and see that it has the largest number for the viscosity, which means it's going to flow very slow. All right, so viscosity, motor oils, they talk about viscosity, and it is about how thick it is and how it flows out of the bottle. All right, so well, here's glycerol. So you got water, you've got your glycerol, which has 3 OHs, and then you got methanol with 1 OH. And you got water with 2 OHs. They didn't make this one green, but water has an OH here. It only has 1 O, but it's got an OH on both sides. And then here you have 3 OHs. So what you would predict, and this only has 1 OH. So this has the most hydrogen bonding. And this has the least H bonding. All right, so you have 1 OH versus 2 OHs versus 3 OHs. All right, and so this would have the highest boiling point of the 3, and this would have the lowest boiling point of the 3. And then that would also go with viscosity. So the higher the boiling point, that means it has a lot of things holding it together. It's going to have the greatest viscosity. It's also going to have the lowest vapor pressure. So this has the highest viscosity, and it's going to have then the lowest vapor pressure. So it takes a lot of energy to get it to vaporize. So at room temperature, it's going to have a very low vapor pressure. All right, so those will go together. Your highest boiling point and your highest viscosity would be very consistently the same. And then that would also give you the lowest vapor pressure. So this always goes together. The highest boiling point is always the lowest vapor pressure. Viscosity, kind of, there's some exceptions to that one. There are no exceptions to the highest boiling point has the lowest vapor pressure. This is always true. And that means that the lowest boiling point is going to have the highest vapor pressure. All right, so lowest boiling point, highest vapor pressure always goes together. Highest boiling point, lowest vapor pressure, that always goes together. Viscosity is about how it flows out of a bottle. Normally that lines up with the highest boiling point, but not always. All right, so here's the hydrogen bonding. If you didn't like my picture, they draw it. The electron pair of your oxygen is interacting with a hydrogen off another water molecule. And then down here, you have an oxygen of another water molecule. They don't show this one. I don't know why not. It's going to interact with the oxygen of another water molecule. And so the one water molecule will have 4 hydrogen bonding interactions. All right, so we look at boiling point. All right, so we have our column in our periodic table. It goes oxygen, sulfur, selenium, and tellurium. So you have your row, your column with oxygen. And so your H2O has the lowest mass. And so it has the fewest London forces. All right. Except, and then all of these are bent. So they are all bent. So they're all polar. So they all have London and dipole-dipole. All right. Now note that only water has hydrogen bonding. So your hydrogen bonding interaction is a very strong intermolecular force. So here's your boiling point. You know water's boiling point is 100. Then you go down to H2S. The boiling point of H2S is minus 60. So that hydrogen bonding, and there's 2 of them for the 2 OHs, increases that boiling point by 160 degrees Celsius. So it's a huge intermolecular force. Now, when we go to H2SE, it goes up higher. It's to minus 40. And this is because larger has more London. And so your H2S has less London forces than the H2SE. And so that has a higher boiling point because once you get to H2S, H2SE, and H2TE, they all have the same London and dipole. All right, and so your London forces are increasing as your mass increases. So go to H2TE, and now your boiling point's at 0. But this is a very clear indication that hydrogen bonding is a huge intermolecular force. If it would not be hydrogen bonding, then your H2O would be at minus 80. All right, so hydrogen bonding is a huge intermolecular force. All right, so then we look at the other columns on the periodic table. When we look at the halogens, all right, so HF, that's hydrogen bonding. All right, so this hydrogen bonding versus HCl. HCl down here is at whatever, minus 80 something, and HF is at 20. So it is a 100-degree temperature difference because of hydrogen bonding. And then your HBr goes up higher because it's larger, more London. HI is even higher than that. Again, larger, more London. We look at the nitrogen column. Nitrogen, NH3, boiling point is about minus 34-ish. And then your pH3 is down here at about minus 90-ish, right? So your NH hydrogen bonding only increased the boiling point about 60 degrees Celsius, versus the H2O went up 160 and HF went up about 100. All right, so your OH bonding is much stronger than your NH bonding. All right, so the hydrogen bond OH is much stronger than your NH hydrogen bond. And then again, pH3, ASH3, SPH3, they are increasing because they're getting larger and more London. So then we go to the carbon. And now we note that carbon does not have hydrogen bonding, and so it is the lowest boiling point in that group, minus 160. And then it increases because SiH4 has more London forces. So now you're at minus 110, GeH4 up to minus 90, SnH4 goes up to minus 50. All right, and so that is just from London forces going up. All right, and also note that these are all non-polar. So all of these are non-polar. These are tetrahedral, perfectly symmetrical. And so these are London only. All right, whereas your NH3, trigonal pyramidal, these are all polar. So up here, these are all polar. So they have both the London and dipole-dipole. But in this column, these are all tetrahedral, perfectly symmetrical, non-polar molecules. And you're only looking at the London forces. And as you increase the mass, you increase your boiling point. All right, so intermolecular forces. All right, so oxygen is simply O, double bond O. All right, and so this is a linear, non-polar, London only. H2O2, here you have two bent oxygen. So this is anytime you have an oxygen with two bonds and two electron pairs, it is bent, and so it has London. It has dipole-dipole. And of course, when you see OH, you have hydrogen bonding. And in this one, everything has London, so London. And this one is very large, and so of the three, this has a very high London force. It's got three giant bromines on it. And so here you draw the tetrahedral, and you know that bromine is the largest electronegativity, and hydrogen is the smallest electronegativity. And so you have a polar molecule. So this is London and dipole-dipole. All right, so the only things that are nonpolar are the ones that are perfectly symmetrical. All right, so this is just identifying the intermolecular forces. Since the H2O2 and the CHBr3 are nowhere close in molar mass, it would be difficult to predict which one has a higher boiling point. This one has OHs, so you would say this one, but this one has three giant bromines and a lot of London forces. Does that override the H bonding? All right, so that is not a question that you would get. Any questions you get are going to be to similar molecules. All right, so then we're going to have different types of solids. You're going to be asked to identify a molecular solid, a metallic solid, an ionic solid, and a covalent network. All right, so a molecular solid is any atom that has been put into a a non-metal that has been put into the solid state. So this is for non-metals. So non-metal elements that have been solidified, and also molecular compounds. Remember, to make a molecular compound, that would be a non-metal with a non-metal. All right, so two nonmetals, H and O, two nonmetals. Water is a molecular compound. You freeze it into ice. That is a molecular solid. CO2, carbon, oxygen, both nonmetals. Dry ice, a molecular solid. All right, if you want a metallic solid, you simply take a element off the periodic table that's a metal, and you make it a solid. So this is just metals on periodic table. All right, so iron, copper, silver, gold, you can keep going, all the metals. That would be a metallic solid, any metal on the periodic table, metallic solid. Ionic solid, remember, to make an ionic compound, ionic means you're going to take a metal with a non-metal, or any polyatomic ion. So sulfate, chlorate, all the nitrate, all those that we talked about, any of those that make a solid, all of those will be ionic compounds, and that would be an ionic solid. All right, so a covalent network is something that you cannot easily make a formula for, like diamond, which is a three-dimensional structure of carbon. Graphite, also a three-dimensional structure of carbon. Asbestos, which has a very complex structure. All right, so if it's something that has a very complex structure, then it's going to be a covalent network. All right, so here's your diamond, here's your graphite. That is a covalent network, not a simple molecule, a very complex molecule. All right, so here's a bunch of solid types. So here we're going to start off with a bunch of molecular solids. So these are all nonmetals like neon, hydrogen and sulfur, carbon, hydrogen, chlorine, hydrogen, oxygen. Acetic acid, remember that it was made with acetate, but acetic acid is a weak acid. Weak acids stay together, they do not ionize. And so acetic acid is a molecular solid. And you'll notice the melting points, minus 249, minus 86, minus 64, 0, 17. All right, so these are very low numbers for melting points. Boiling points also relatively low boiling points. This has low melting and boiling points. All right, so now we go to our metallic solids, and the mercury, sodium, tungsten, just metals off the periodic table. Now, mercury, remember, is a liquid at room temperature, and so it doesn't freeze until you cool it down to minus 39 degrees Celsius. And then we look at tungsten, which is used in light bulbs. It has a melting point of 3,410, a huge range in melting points for your metallic solids. Also a huge range for your boiling point, at 357 all the way up to 5,660 degrees Celsius for tungsten. All right, so these have varying melting and boiling points. Ionic, all right, so this is ionic compounds, so cesium chloride, sodium chloride, magnesium oxide, metal with a non-metal. All right, so these are relatively high melting points and high boiling points. So these have both high melting and high boiling. And then we have quartz, which is a polymerized SiO2, silicon dioxide. that is a covalent network because there are many, many, many of them. It is not silicon dioxide, the compound. It is the polymer of silicon dioxide, and that is quartz. And also diamond. These things are very, very high melting points and very high boiling points. All right, so this is just a chart of a few different types of your solids and how they vary in melting and boiling point. All right, and then metals, of course, this is from chapter 1 or 2. Good electrical conductors, because of delocalized valence electrons. There's copper wires in every building. Copper is an excellent conductor of electricity. And ionic solids do not conduct electricity. However, if you dissolve them in water, then they will conduct electricity because they have ions in solution. All right, and so here is then the property chart. So we went through it a little bit. Molecular, the melting points were low. Metallic, the melting points were variable. Ionic, they were high, some very high. Covalent network, all of the melting points were very high. Some other physical properties, when you look at dry ice, you look at just regular ice, they're soft and brittle. All right, so you can break them easily. And they are non-conducting. Molecular compounds do not conduct electricity. Your metallic has variable hardness. All right, so because they're in the liquid state sometimes, and then you've got the iron rod, very, very hard. And they're malleable, which means they can be pounded into sheets. They're ductile, drawn into wire, and we draw them into wire because they are very conducting. And we use that for conducting electricity. Ionic, they're hard and brittle. So now if you got a salt block for deer, cow, whatever, they're hard and they're brittle. You can hit them with a hammer, they will break. They are non-conducting as a liquid, but you put water with them, and now they are conducting. And your covalent network, just think of a diamond, very hard, and usually non-conducting. So you will need to know the properties of the 4 different types of solids. All right, so you can get a solid that has a crystalline form. And so this is a well-defined ordered structure in 3 dimensions. So this is a 3-dimensional structure that is very well-defined. An amorphous solid is one that has a lot of distorted structures. So an amorphous solid does not have a well-defined arrangement of the unit cell. So glass is an amorphous solid, does not have a well-defined 3-dimensional structure. All right, so then we're going to talk about a crystal lattice. All right, so here is copper. Now, when we do a crystal lattice, we're going to only talk about cubic crystal lattices. All right, so we're going to look at this cube. So this is a corner. When you are a corner, 1/8 of this sphere is inside of your cube. This is a face. All right, so a cube, of course, is a dice. You roll a dice, you get a 1, 2, 3, 4, 5, 6. There are 6 faces on a dice. And 1/2 of this sphere is inside of the cube. The other half is outside the cube. Right? And so when you look at your copper, there is, you have your copper atoms on each face. There are 6 faces. 1/2 inside of the cube. So that's 3 copper atoms. And then you have the 8 corners. So all cubes have 8 corners. You can count them 1, 2, 3, 4, 5, 6, 7, 8. 4 corners, 6 faces. 8 corners, 6 faces. You got 4 corners on top, 4 corners on bottom. All right, and so you have 1/8 of that atom inside of your cube. So when we're looking at this copper structure, there are 4 copper atoms in the cube. All right, but your faces and your corners are not the only choice. There are 2 other choices. If we had one here, this is called an edge. If it were here, that would be an edge, and 1/4 of your atom would be inside the cube if you were on the edge. If you were in the center, that one is called the center. If you're in the center, the whole thing is in the cube. So if you're in the center, the whole sphere is in the cube. All right, so there's 4 choices when you have your atoms, which are spherical. You're either going to be on a corner, 1/8 of it's inside the cube, a face, 1/2 of it's inside the cube, an edge, 1/4 of it's inside the cube, or it's actually in the center where the whole thing is in the cube. We are only going to talk about the cubic, but there's also tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, and triclinic. In this class, we are only going to talk about the cubic crystal structures. All right, and so all of your angles are 90 degrees. It's a perfect cube. Your length, your width, your height, they're all the same. And so since they are the same, we call them all the same. So we say A is, so the length, the width, the height is all the same. So I keep it the same, and it is A. I call that all the same as the same letter as A. All right, so here are the 3 possible cubic structures that we will get. We will get the simple cubic, where there's only atoms on the corners. So we have 8 corners, 1/8, so 1 atom in the cube. So when we're looking at a simple cubic structure, there is only 1 atom that's in the cube. Body-centered, this is the 8 corners times 1/8, and 1 in the center. The whole thing is in there. So there's 2 atoms in the cube. When you look at face-centered, you have your 8 corners, and you have your 6 faces. And when we had our copper before, that's what we had. We had a face-centered cubic. And so we have 1 and 3, so there are 4 atoms in the cube. So face-centered is 4 atoms. Body-centered is 2 atoms in the cube. And simple cubic is 1 atom in the cube. All right, so you need to know that about the simple, the body, and the face-centered cubic. You're going to be given an equation to find the radius of the sphere. All right, but you're going to be given 3 of them. So you have to know which one goes for the simple, which one goes for the body-centered, and which one goes for the face-centered. All right, so the red line here is a radius. All right, so I need to know that length. All right, and this is also a radius. All right, and we also know that the length that goes from top to bottom is A. And so this one is very simple. The edge, A, is equal to 2R. So you'll either be given the equation solve for A, which is 2R, or it'll be solved for R. R is equal to A over 2. All right, so you're going to be given a radius equation. If it's A over 2, well, that is for the simple cubic structure. All right, and then we're going to go over to face-centered because face-centered is a simple geometry equation. All right, I'm going to make my triangle here. All right, so this is A, and this is A, and this is the hypotenuse, which is a radius, and then a diameter, which is 2 radiuses added together, and then another radius. And so I see that the hypotenuse here is 4 radiuses. And so I can solve this geometric equation. I have a squared plus a squared is equal to 4r squared. That is Pythagorean's theorem. A squared times b squared equals c squared, where c is your hypotenuse. Here, a and b are the same. It's a cube, so it's a times a squared plus a squared. And then your hypotenuse, c squared, is 4r. And so we square the 4r. And so then we have to solve for a, and then solve for r. And so we have 2a squared is equal to 16r squared. Now we're running out of room. Okay, so then we divide by 2. And then we get a squared is equal to 8r squared. And then you take the square root of both sides and you get a is equal to 2 square root of 2r. All right, so again, you're going to be given 3 radius equations. All right, you can easily solve for the cubic. That is the simplest one. And then a simple geometry equation will get you the face-centered. All right, and then here is much more difficult because I can't draw it on here because I need to go from this corner to the back corner, which you can't see, which is 4r. And so I need this distance. And then I need the distance, again, that you can't see that goes back there. All right, so this one is, you can't do it well in 3 dimensions. All right, so anyway, so it's the other one. We'll just go with, it's not the simple, it's not the face-centered, it is the body-centered. All 3 equations are given. You will have to know which one to use for simple, which one to use for body, and which one to use for face-centered. You have to do the Pythagorean theorem twice to get the body-centered cubic. It's not that difficult, but it's not as easy as simple, and it's not as easy as face-centered. So I just say, if you forget, well, you know you can solve the simple, you know you can solve the face-centered, and so the other one is the body-centered. All right, so if you are body-centered, you're going to have 68% of your cube is going to be occupied by atoms. Remember, body-centered, you have 2 atoms in the cube. When you do a cubic closed packed structure, okay, this is going to be the face-centered. So your face-centered is going to give you 74%. That's 4 atoms in the cube. And then simple will give you a 52%, and that is 1 atom in the cube. If we go back and we see, you can't really tell, but anyway, there's a lot more empty space here, and so 52% of the space has the spheres in it, 48% is empty. Here, your body-centered, 68% is with the spheres, and then, of course, then the rest of that, 32% is empty space, and then here, your face-centered, 74% is occupied by the spheres, and then the other 26% is empty space. So you can see that there's empty spaces in all of these cubes. All right, if we look at the crystal structure of cesium chloride, all right, we have our blue cesium, and so that one is in the center, so the whole thing is in there. So you have one cesium atom in this structure, in this cubic structure. Then you have the chlorines at each corner, and there are 8 corners. So you have the green chlorines at the 8 corners. Again, 1/8 is inside of the cube. And so you see that you have one cesium and you have one chlorine, and we know from the periodic table that cesium is going to be in the +1 column and chlorine is in the -1 column. And so when we have our solid, we know the structure is going to come to a cesium chloride 1-to-1 in the cubic structure. And so here we have the 8 corners for 1, and in the center for the 1 cesium. All right, if we look at sodium chloride. Now, what we do know is that sodium is +1 and Cl is -1, and so we're going to get NaCl. But you can't say 1-to-1 because that is not what they are showing here. We do know that the simplest ratio is going to be 1-to-1. All right, so the sodiums are on the edges. All right, so this is an edge. But remember, 1/4 of your sphere is on the edge, 1/8 on the corner, 1/2 on the face. All right, and so we have our structure here where we have 4 edges, another 4 edges, another 4 edges. All right, so we have our 12 edges. All right, so that is 1/4 each. So we have 3 on the edges that are inside of the cube. All right, so then we look at the chlorines here. We got 8 on the corners. And we have 6 on the faces. All right, so the one we can't see is the sodium. So this is sodium. So the one that we can't see is the sodium in the center, and then there's one in the center. All right, so if you come over here and you look at corner, green corner, green corner, green corner, green corner, all right? And then you come down here, you got green corner. Oh, they're doing the other one. Of course, they are not doing the other one. Okay. Green corner, green corner. Okay, so we have what I'm trying to put in here are the green corners. And so this corner is right there, and this corner is right there. All right, and then this edge is right there. Okay, so they're just, this is the space filling view, and this is the open view. All right, and so our unit cell that we're looking at over here goes from here down to here, over to here, up to there, back to there. Okay, so this is the unit cell that we're looking at. All right, so, all right, you've got your 1, 2, 3, 4 edges, and then you got your 1, 2, 3, 4 edges again, and then you got your 1, 2, 3, 4 edges again. All right, so hard to see, but this one we didn't circle. This is in the center. Of course, you can't see the center in the space filling model. You cannot see the center. So it either has to tell you that there's one in the center, or they have to show you another picture to show that there is another sodium that is in the center. All right, and so you have 4 sodiums and you have 4 chlorides, and that is a NaCl lowest ratio, 1 sodium to 1 chlorine. All right. Each corner, each face has the center. All right, so each corner and each face and the center has the S-2 ion. All right, so you can look over here and you can see that, but it's easier to look it over here and say each corner, okay, 1/8 times 8, that's 1. Each face, 1/2 times 6, that's 3. And the center, which is 1. And so you have an S-2. All right, and so that would be your 5 S-2s. There are also 4 Zn+2 ions completely within the unit cell. All right, so there are 4 Zn+2s completely inside within the unit cell. This gives a total of 4 Zn+2 and 4 S-2 ions. Not if they're saying that correct. All right, so let's look and see what they have wrong. They have the corners. Down. All right, so there are the 8 corners. And then the faces. There are 6 of them. 1, 2, 3, 4, 5, and 6. I didn't do the 8 corners. All right. All right, so there's each corner and each face. So that would be 8 and 6. There would be 14. If you count the yellow, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There are only 14. All right, so this is wrong. All right, so that's each corner and each face. All right, and so each corner, that would give you 1. Each face, that would give you 3. That's your total of 4. And then your black ones that are completely inside of the structure. This one is kind of hidden back here. And so you have your 4 Zn+2s and your 4 S-2s. And so again, you knew that -2 and +2 is going to be a 1-to-1 ratio, and it is 4-to-4, which reduces down to 1-to-1. Your simplest ratio is ZnS. All right, so your cube volume is a cube. All right, your sphere volume is 4/3 pi r cubed. All right, and so the volume of your cube, which is equal to a cubed all right, so this is a made-up equation. I made up the equation, but I didn't make up the way to remember it, which is also genius. So you have your volume of the cube, which is length times width times height. So cube, they're all the same, so that's a cube. And that is equal to mammal DNA. So now M sub M, that's how I remember it, mammal DNA. M sub M is your molar mass, and that's in grams per mole. L is atoms in the cube. All right, so again, simple. L is equal to 1. Body, L is equal to 2. Base, L is equal to 4. So those are your three choices for L. It's either going to be 1, 2, or 4. It's either going to be a simple. We're only doing 3 of the types of the crystal lattices: the simple, the body, and the face. So 1 atoms in the cube, or 2, or 4. D is density, and that is in grams per centimeter cubed, because that's how we're going to get a cube. That's going to be our centimeter cube. And then Na is, of course, Avogadro's number, 6.022 times 10 to the 23rd. And this is going to be atoms, which is what you have here, atoms in the cube. It's going to be 1 atom, or it's going to be 2 atoms, or it's going to be 4 atoms. And how we're going to get that to cancel is from our Avogadro's number, atoms per mole. And the moles cancel because you have your molar mass. And so A is equal to the length of a side. And in this equation, it's going to be in centimeters, because that's going to match your density. This matches this. All right, now we're going to have to convert to angstroms. The answers are almost always given in angstroms. Remember, 1 angstrom is 1 times 10 to the minus 10 meters. So an angstrom is also 1 times 10 to the minus 8 centimeter. All right, so you need to know an angstrom is 1 times 10 to the minus 10 meters. You can then convert that to centimeters, which is 1 times 10 to the minus 8. All right, so when you're given a question and it says that A is equal to 3.152 angstroms, you should immediately change that to A is equal to 3.152 times 10 to the minus 8 centimeters. All right, so you want to convert your angstroms into centimeters. Then all of your units work out just as planned up here. And then note also, if you're getting the volume of your cube, that is going to be in centimeters to the third. All right. So what I would do is I would solve for A, and I would get A, and then I would convert A, which is in centimeters, into angstroms, and then cube that. Depends on what units you're asked for. If you're asked for angstroms or centimeters, most of the time they're going to ask for centimeters, but they're going to give you angstroms for a length. So make sure that you can easily convert your length in angstroms to centimeters. That is going to be very important for this type of problem. All right, so let's do a problem. I have, let's say I have a body-centered with a edge length of 3.152 angstroms. And I have a density of 3.75 grams per milliliter. Again, you have to know that then from before, a milliliter is equal to a centimeter cubed. Normally they give it to you in centimeters cubed, but if it's a milliliter, you have to know that that is a centimeter cubed. All right, calculate the molar mass. All right, so this would be a problem where you would use your volume, which is equal to A cubed, which is equal to mammal DNA. All right, and so what you have to do is make sure that this is centimeters cubed, and this, in order for that to cancel out, needs to be in centimeters. So times 10 to the minus 8 centimeters. So get rid of your angstroms. This unit here and this unit here must match. Centimeters is what I will always use. You feel free to convert your density into grams per angstroms cubed. That would be a lot more work, but you can do it that way. All right, so volume is equal to A cubed. All right, so that is equal to mammal DNA. So we have what we need. We know that A is right here. We know that the molar mass, that's what we're looking for. L, body-centered, L is 2. Density is given, 3.75. Avogadro's number is a constant, and we have A that we can cube. And so we have everything except for the molar mass. And so let's plug in our numbers. 3.152 times 10 to the minus 8 cubed is equal to the molar mass times number of atoms, which is 2, density 3.75. Probably put in our units. And then we have our Avogadro's number, 6.022 times 10 to the 23rd atoms per mole. All right, so the moles cancel. No, the moles don't cancel. The atoms cancel. Atoms cancel with atoms. When you solve for this, all right, so let's solve this. And then we will cancel our units. So we have 3.152 times 10 to the minus 8 centimeters, and we're going to cube that. Multiply both sides by 3.75 grams per centimeter cubed. Multiply both sides by 6.022 times 10 to the 23rd. Divide both sides by 2. And that is equal to the molar mass. All right, so now we can see the units canceling. So the atoms cancel the atoms. The centimeters times the centimeters times the centimeters. The centimeters cubed is going to cancel the centimeters cubed. And we are left with the units, grams per mole, which we will be giving to 3 significant figures. Atoms are a perfect number. So 1, 2, 4, that's an integer. Those are perfect numbers. We grab our calculator. 3.152 times 10 to the negative 8 raised to the third. All right, and so this number is 3.13154478 times 10 to the minus 23rd centimeters cubed. Of course, that should only be 4 sig figs, but I don't clear out my calculator and round it. I round my final answer will have 3 sig figs. I multiply that by 3.75. I multiply that by 6.022 times 10 to the 23rd. And then I take all that, divide it by 2. And I get 35.5. All right, and so this was a made-up question, and then I would say, what atom is it? And then you go to the periodic table, and you would see that this would be a chlorine. However, this doesn't make any sense because this is for metals. But anyway, I made up the numbers, but this is the answer you would get, and then this would match the element on the periodic table. So what element does this match? And the element would be a chlorine. All right, so you're going to have a molar mass, you get your periodic table, and then you line it up with the molar mass of the element, and then that's how you would get what the element was. Okay. All right, so there's going to be a number of questions on the homework that are going to ask you a lot of these different variables. They're going to ask, is it body-centered, face-centered, or simple? And that's all about L. You solve for L. 1 is simple. If you get 2, it's body. If you get 4, it's face. They'll have a question just like this. Give you all this information, ask for the molar mass, and then identify the element. Go to the periodic table once you have your molar mass, identify the element. Sometimes they'll give you the molar mass, which is they'll give you the identity of the element, which you have the molar mass. They'll tell you if it's simple body or face, you have the L. They won't give you the density. They'll give you a size of the length, and of course Avogadro's number is a constant. They'll have you solve for density. So there's, of course, the variables are you can solve for A. All right, so if they give you the molar mass, the type of structure, and the density, you can solve for A. You can solve for density. You can solve for molar mass. You can solve for the L value and see if it is a face, body, or simple crystal lattice. So you're going to have 4 variables here. They have to give you 3 of them. All right, so you have to be given 3 of the 4. So if I gave you the L, the density, and the A, that's what I gave this time. You can find the molar mass. Again, you have to be given 3 out of the 4 and solve for the 1 unknown. There cannot be more than 1 unknown in these types of problems. All right, but there will be a number of problems that will be using this equation. All right, we will do chapter 12 the next 2 days, and then we will be done with new material. There's no